Okay, so I'm going to get started. Today's announcements are the exam is tomorrow night, exam 1. I am not planning on finishing chapter 3 in time for the exam, so I am going to cover today up through the end of page 6 in the notes. So everything through there is fair game, but I won't cover page 7 and 8 from my notes. So anything that involves comparing acid-base strength based on structure, where it gives you two molecules and says, like, circle the stronger acid or the one with the higher or lower pK or whatever, that will not be fair game for this exam. But it will be fair game for exam 2, so you're not off the hook. You just are, I guess, temporarily reprieved from it. Okay, other announcements are chapter 2 saplings due 9 a.m. Wednesday. Yeah?
What time is the exam again?
7 to 9 p.m., Chem 140. Yep, welcome. Okay. All right, so what we're looking at right now is using arrows to show resonance still. Okay, so a reminder here, we still got to follow the same 3 valid moves that we had for any other arrow pushing. So it's got to be either lone pair to bond, bond to lone pair, or bond to bond. But we're further constrained than we are with normal arrow pushing because we also can't break connectivity. So the same 3 normal moves as arrow pushing, but can't change connectivity. So basically, lone pairs and pi bonds are all we get to play with. Because if we moved sigma bonds, we'd change what's connected to what. Okay, so only lone pairs and pi bond electrons we're allowed to move. So I put up one sort of very small example of how that might look, but this actually turns out to be a very, very common motif in a lot of other more complicated molecules that do resonance. And that is this 3-atom subunit where you've got a double bond between 2 atoms and then a positive charge on the third. So this is a region of low electron density. We know that because of the positive charge that's missing electrons. So we can show these pi electrons moving over to here. And forming a positive charge there. So even though this is a mirror image of the same thing, looking for this 3-atom subunit in bigger, more complicated molecules, anytime you have 2 atoms that are double bonded and then the third with a positive charge, looking for that as part of a bigger molecule will make it a lot easier to show resonance. Okay, so I did that one last time. What I didn't get to is we can actually do something sort of similar if we have a negative charge there instead. So now, instead of being low electron density, this is actually high electron density. It's got too many electrons. So instead of going to this end of the molecule, electron density is going to come out of here. So we're going to show these electrons going to here and kicking over to the left end of this molecule. So again, make sure you use the resonance arrow. That means a very specific thing here, and it's important to show. So even though the arrow pushing looks different, we're going right to left instead of left to right, we still end up sort of making a similar change to the molecule. We've got a 3-atom subunit, 2 atoms double bonded, one with a charge, and we flip which end is which. Okay, so if you're given a more complicated molecule, something like this, for example, what you want to do is look for those 3-atom subunits where you've got a charge, and then that's right next to 2 atoms with a double bond. So I'm going to shade this in here. All right, there's our 3-atom subunit for this form. We can do the same arrow pushing we did up here, hop those electrons over to the positive charge, and we can get another resonance form out of it, where everything else is unchanged, but we've flipped which end is which of that 3-atom subunit. Okay, so now we're at this resonance form, and again, we can look for a different 3-atom subunit. We could use the same one and push it right back to where we started, but that's not meaningful as drawing another copy of the same thing. So instead, I'm going to look for that one now, show resonance, where I do exactly the same arrow pushing as I did in that real simple example. And that gets me to here. And then same thing, another 3-atom subunit exists down here. Can do the same thing. And that gets me to here. And now I got another one going up here. Which gets me to this, which is pretty similar to where I started, only the double bonds in the ring have all shifted around by one. So this one has 1, 2, 3, 4, 5 discrete resonance forms. Okay. So I'm doing these as like the simplest possible move to get from one form to the next. A question?
How do you decide that this is like the pattern you go in? Like, why not take the bottom pi bond and move it somewhere at the same time or on?
Excellent question. So that's actually exactly what I'm about to get at, is that, so I'm showing like the simplest move to get to the next form, like only one arrow, but you can always go from any valid resonance form to any other resonance form if you just combine arrows. So you get from any form to any other form. So say I'm starting at this one, and I want to show in one step how to get over to here. I can start out by drawing this. And I'll just draw the product up there so I don't have to keep looking. Okay, so I know that the 2 arrows that I use to get over to that second boxed form, I have to have one from this double bond kicking up, and I have to have one from this double bond kicking over. And so if I use both of those, I'll go straight from this form over to here. We can also show arrows moving for like any one over here, like in the reverse direction, and in that case you just do like the arrow going back from the new double bond into the new positive charge. So you should always be able to get from any resonance form to any other resonance form. It just might take more arrows depending on how different those forms look. Okay, does that?
Why do you not just move like the bottom pi bond?
I see. So you're asking like, what if I start at, say, this one? And then why don't I just like do something like that where the pi bond splits on its own? So that is valid arrow pushing. So in this case, I'm taking electrons out of the pi bond. I'm dropping both of them onto this carbon. So what charge is this bottom carbon going to have? Negative, right? Yeah. And it's got a lone pair on it. What charge is this one going to have? Positive, right? Because I'm taking electrons away from it and I'm not giving it anything in exchange. So this is valid arrow pushing, but I would not show this as one of the major resonance forms. And I have to be careful about my wording on the exam question here, because if I say show every resonance form for this molecule, you can get up to a whole bunch of stuff that looks like this, and there's like dozens and dozens of different things you could do to it. But major resonance forms, this goes back to like that list of resonance rules that I wrote up like towards the end of last lecture, where the fewer charges you have, the more stable the molecule is. So even this is like a thing you could do. How stable is this compared to all the other ones up here? Like not very, right? There's a bunch of charges on it. So not stable enough too many charges. So you would not show this as a major resonance form. Sorry, I'm like, just got enough room there. Not stable enough, too many charges. Okay, so there's a bunch of things you could do, but in general, if you want to minimize the total number of charges, you're probably going to stick to frequently moves that look like this 3-atom subunit shuffling around. So look for those first, and then if you're not seeing any there, then you can start playing around with like splitting bonds in weird ways too. And we'll look at some examples of that in just a second here. But any questions of this before I move on? Okay, cool. So one other thing that's worth pointing out on this particular example real quick is that anywhere the plus charge exists during any resonance form, we know that we can average together resonance forms. We've seen that on like simple examples in chapter 1. Now that we have forms that are straight up different molecules, or that look like different molecules, even though resonance means they're all averaged together, it's no longer an unweighted average. Like some of these forms might factor more heavily into resonance than others do. So we can average together these forms, but now it's a weighted average. And we don't know how that weighting is going to look. We can guess sometimes, but we can't calculate exactly like this atom has 3/5 of a positive charge or anything like that. Okay. So what we can show is, so the sigma framework stays intact the whole time. Anywhere where we have a double bond during any of these resonance forms, we can show as a dotted sort of partial second bond. Sorry, give me just 1 second. So this is a double bond at some of the time, like during at least 2 of the resonance forms. This one is a double bond some of the time, double bond some of the time. This entire ring actually, at some point, all of those bonds are double bonds. And then we can show charges on any atom that has a charge during any of the resonance forms. So that's delta positive. No, there's never a charge on here, but there is here, and here, and here. So I don't know exactly how much of a charge they are, and maybe some of them carry that plus charge more of the time, but we at least know like alternating atoms are going to hold plus charges in this form, which sort of makes sense, right? Based on that 3-atom subunit, you can never put the plus charge in the middle. It's always at one end or the other. So you should always expect charges to sort of alternate and skip a carbon in between the locations where they hang out. Okay, getting back to your question in the back.
Is there a way you can know how many resonance structures you have?
Not really. A lot of it is just like shuffle electrons around until you run out of options. If you do have like a sort of continuous chain like this, like going around the ring, then that might sort of give you some ideas. And a lot of the time, since it's this alternating carbons bear the positive charge thing, at some point you just run out of places to put it unless you want to put them next to each other, which you can't do. At least like in the 6-membered ring, you can't go around the ring and get them on every carbon. So, yeah. Because some of these places might be better for a positive charge to live than other places. So like, we'll cover this a little bit more in the next chapter, but it turns out the more carbons you have, like the more substituted it is, the better it is at holding a positive charge. And so like, I guess maybe not on this particular example because all the delta positive ones are secondary, but maybe like if one of them were tertiary, the positive charge would actually spend more time there, so you wouldn't know exactly like how much that holds the positive versus the other ones. So, yeah.
So this is kind of going back to stuff on the top board. So on the exam, you only want to see up resonance structures that have least amount of charge. So should we just basically look for all the structures where we only have like one circle or maybe 2 circles?
Yeah, so pretty much like you're never going to be able to get lower than like the overall charge on this thing. So if you got +1, then you pretty much every form has to have at least 1 charge. Yeah, but try not to like add any more in than that if you can possibly avoid it. So yeah, good question. Okay, so other questions about this one? Okay, cool. Okay, so let's look a little bit more about sort of analyzing relative stability. So this is looking at the last two rules that I wrote up last time. Just as a refresher here. Maximizing the number of atoms with filled octets is more important. So you want to maximize having the most filled octets first. Then you want to look at minimizing charges. And then if LS is still equal between forms, then you want to put negative charges on more electronegative atoms and vice versa. Or positive charges on less electronegative atoms. Okay, so I've sort of got three different things, but we want to prioritize octets over charges. Okay, so here's one example. Even though that's not an oxygen, actually, that should be a carbon. All right, so that's a carbon with a lone pair and a negative charge. So even though not all three atoms here are carbons, it still has that same three-atom subunit that we saw as an example up here. So again, I can take that lone pair, kick it over, boot up the pi bond electrons to the end of the three-atom chain. And show this resonance form over here. All right, so quick check. How many atoms with unfilled octets do I have in this whole structure? 0, right? I think I heard a few people whisper that. How many atoms with unfilled octets do I have in this whole structure? Also 0. Okay, so that's tied. Okay, so both have all filled octets. Total number of charges, 1 minus charge, 1 minus charge, the same. But the only difference between them is here negative charges on carbon versus here negative charges on oxygen. So left or right, which one's going to be more stable? Yep, the right one. Because here, since oxygen is more electronegative than carbon, this one's going to be the dominant form. So it might not be that huge a difference between them. Like they're pretty tied in other regards, but this is still going to be contributing more to the resonance form. The average together version is going to look more weighted towards this end of things than it does towards this end of things. Okay, so questions about that example? Yeah.
So, I understand that's the most stable one, and the other one is less stable, but it still averages into the resonance form.
Yeah, so when you're averaging these together as a weighted average, like this is going to weight more heavily, this is going to contribute less, but it's pretty close, so it might be like a, I don't know, 75% of the average comes from this, 25 from that sort of a deal, where...
I'm wondering if the benzene that you showed earlier with the 3 parts, would that also weigh into the average of that molecule's resonance forms?
This one up here?
Yeah.
So...
Really unlikely.
Yeah, so it might, but like sub 1%, I would say. And so like it's unstable enough that I would say like definitely not a major resonance form. Yeah, so I guess like, in terms of where to draw the cutoff between major and not major resonance forms, I'd say like if all the difference between them is just like where the single negative charge or positive charge is, then probably they're both going to be close enough that I would consider them both to be major. If you have like some big increase in the number of charges, that would be one thing. Or if you have like an increase in the number of unfilled octet atoms, that would be another thing that would, both of these rules, either one of them getting broken would probably render it something that's not major enough to be worth drawing. I guess like that actually goes back to this thing. Not only does it have more charges overall, but if you look like carbon with a positive charge, that actually has an unfilled octet on it. And so here I've actually gone up to 2 unfilled octet atoms as well. So that's kind of 2 strikes against that one being a major form. Question?
When you're trying the arrows, does it matter that like your first electron push arrow goes to the bond and the second one goes to the atom?
Good question. So for this one, I can either show it going to the bond in the middle, or I can show it attacking the middle carbon. Either one is acceptable, and I think sapling will also let you draw both. So I tend to show it going to the bond rather than the atom, but yeah. Mm-hmm. Okay. Yeah.
Will an unfilled octet always have a positive charge?
On carbon, yes. No, actually, that's not true either.
How do we identify when an octet is not full?
Right. So I guess carbon with a positive charge will always have an unfilled octet, but the other way around is not always true. So unfilled octets examples. So like anytime you have carbon with a positive charge, pretty much the only way to get that is to have carbon with 3 bonds and no lone pair. So that's probably the most common example of that you would see. Boron is another very, very common underachiever as far as octets. This one really tends to have like 3 bonds to be neutral, in which case it has an empty orbital. So we'll often see like things attacking a neutral boron atom because they've got an unfilled octet there. What other examples will we see? I think that's pretty much it as far as like common examples. I guess you could do some like, no, both the other examples I have in the notes are also like unfilled octet because of a carbon with a plus charge. So yeah, so pretty much these 2. I guess you could do some weird thing where if you want to try like taking this double bond and like breaking it towards the carbon here, in which case you could, if you really wanted to get this going, oof. So for one thing, oxygen has an unfilled octet, and for another, you have a plus charge on the oxygen and a minus charge on the carbon, which is like the opposite of what electronegativity would ask you to do. So I'm wincing looking at that. Let's not do that. Yeah, so that's like, I don't think that will ever come up in any mechanism or reaction that we're going to see in this class, but this is very common. This is reasonably common as well. So, okay, so a couple more examples real quick. Switching to the right board. Okay, so sort of the opposite version. Of what I did down here. This is something that we'll actually see come up in reactions sometimes once we start getting into carbonyl chemistry. So we're not going to break this down towards the carbon. We saw kind of why, but we know the oxygen here has a positive charge because it's got 1 more bond and 1 less lone pair than it would like. So we can actually break the carbonyl up towards the oxygen. Which gets us to here. Okay, so quick check. Number of unfilled octet atoms over here. 0, right? So you might at first glance like jump at that positive charge and say that might be an unfilled octet, but then if you go in and check, you're like, wait, no, oxygen has 3 bonds to it and a lone pair, so it's actually got a filled octet. How about number of unfilled octets over here? 1, right? Yeah. So carbon with a positive charge is an unfilled octet. Okay, so that right there is enough to render this one as the less stable resonance form. This might be slightly counterbalanced by the fact that here you have a plus charge on carbon, which is less electronegative. Here it's on oxygen, which is more electronegative. So it might be not as cut and dried as you would initially expect based on unfilled octet. It's got some mitigating circumstances. So this is more stable, but not by quite as much as it would be if you didn't have electronegativity on your side for this one. So I'd still show this one as like the only major resonance form, but this one is like at least got something to speak for it. So, okay. Other questions about that one? Okay. So one more example from the notes. Okay, so drawing resonance for this thing, I'm going to start with high electron density, so this oxygen here. And so if I kick some electrons into this NO bond, nitrogen's got more than a filled octet. It's going to have to drop something onto carbon. So I'm going to end up at here. Okay, so this looks like a really complicated thing that's happening, but deep down, it's actually pretty much the same as the example that I drew at the very start of lecture with the negative charges. I've got this 3-atom subunit, carbon, nitrogen, oxygen. I've got a negative charge at one end, and I've got, well, not a double bond, but a triple bond over here, actually. But it's still a pi bond in between these two atoms. So I'm taking this negative charge, kicking into the middle, breaking the pi bond over, and so I switch where that pi bond is that moved and which end the negative charge is on. Nothing else about this changes. The second pi bond stays put because I'm not using that. The positive charge on nitrogen stays put because I can't move that. But it's still following the same type of change as that 3-atom subunit with a negative charge. You just have to like ignore all the red herrings and other stuff that's in the way to see it. Okay. So between these two forms, number of unfilled octets in this structure? 0, good. So this is actually a different resonance form than I put in the notes, I'm actually realizing. So I can do that one next as another example. Okay, so number of unfilled octets. So all filled octets. Compared to this one, which, how many unfilled octets are there in here? 0, yep. So this is a different example from the notes. I'll put that one up next. But if you're following along, so we can do multiple things to this form, and I'm just showing like one specific example. Question? Yep.
How does the C with the single and then double to nitrogen, does it have 2 lone pairs? Is that
The carbon actually just has the 1 lone pair here. Yep, yeah, to get a filled octet. Okay, so between these two specific forms of this molecule, they both have all filled octets. So the difference between them is negative charge on oxygen versus negative charge on carbon. So out of those two, which one's going to be more stable? Oxygen, right? So out of these two specific forms, this one is more stable. Okay, so that's one option for what I could have done for arrow pushing. Or, because we know there could be more than 2 resonance forms, and I'm just going to redraw this one down here so it's less confusing with the arrow pushing. What I could have done in the notes instead is just break that bond over onto the nitrogen. So this is different than the 3-atom subunit pattern. I'm still moving just pi bonds though. So I could have drawn my arrow pushing to look like this. Okay, so we already know number of unfilled octets over here is 0. They're all filled. Over here, how many unfilled octets on this whole deal? 1, right? On the carbon with a positive charge. Okay, carbon unfilled, which means that this one is less stable. Okay, so out of the 3 forms I drew, I can actually rank them 1, 2, and 3. This one has an unfilled octet, and neither of the other ones do. So this one is probably going to be least stable. So this one up here has all filled octets. It just doesn't have the charge in as good a place. This one's probably going to be 2. And then this one that I drew 2 copies of is going to be 1. It's got all filled octets, and the charges are in the best place for them. Question?
With number 3, is the electronegativity difference between like carbon and nitrogen, would that help kind of push the other way?
It might a little bit. They're not as different in electronegativity as like oxygen and carbon are, but yeah, that might make it a little bit less bad than it would otherwise be. So, Okay, yeah. There is, yeah. So I can draw it or not. But yeah, if you want to show it, that may help keep track.
So if there's like not a charge on it, could you just assume that what isn't bonded is a lone pair?
Yes, that's correct. Yeah, so charges you always have to show if they exist there. Lone pairs you can show or not, depending on how specific you want to be.
So with what you just said and then the second resonance structure, how do we know that there's that lone found carbon before it's drawn?
This one here?
Yeah, if it wasn't drawn, could we assume that it's there because of the negative charge?
Yep, yeah. So because of the negative charge, I know that carbon has to have 5 total electrons in its octet, which means that gives it a lone pair pretty much by necessity. Yeah. So you can sort of figure out from charges like carbon with a negative charge will always have a lone pair, carbon with a positive charge will always have an unfilled octet, and both of those things will have pretty important consequences for reactivity later on. Okay. So one last thing for resonance arrow pushing. Just box it off over here. And that is that we don't have to have any lone pairs or charges. So we don't always have to follow this 3-atom pattern going on. If we want, we can just use double bonds, pi bond electrons, and shuffle around. And especially for benzene, we can actually do it in a closed loop, so that we just toggle which carbons are single and which carbons are double bonded. So these 2 resonance forms actually are equal contributors, at least on straight benzene, because there's no difference. There's rotational symmetry between the 2 forms. And that's why a lot of the time for benzene, you won't even see people bothering to draw the double bond. They'll just draw a circle in the middle there, just saying that all of these bonds are 1.5 bond order on average. There's actually more to it than that even. There's aromaticity that's going on that changes things, but benzene a lot of the time you just see as a hexagon with a circle. Okay, questions about that? Okay, cool. So that wraps it up for arrow pushing resonance. The last part of today we're going to look at evaluating acid bases. Okay, so we've already seen that use curved arrows to go do the attack. If you're specifically attacking a proton, that's an acid-base reaction. So let me throw something up here. Okay, so an OH minus here. Here's high electron density. Technically the nitrogen has low electron density, but if we just go in for the nitrogen, we're not really helping it out because it'll have to drop something else and it's not getting its lone pair back that it really wants to be neutral. So instead what we're going to do, take an H here, and that forces the H to drop the bond, which goes and becomes a nitrogen's lone pair, which makes the nitrogen neutral. Okay. So we get to nitrogen here with 3 H's and a water molecule, H2O here. Okay, so out of the left side of this equation, the starting materials, which one is the base, the NH4 plus or the OH minus? OH minus, because it's taking a proton. So that's my base, which means this must be my acid. And I know that they're acid and base instead of nucleophile, electrophile, because this is specifically a proton transfer, right? I'm specifically coming in, throwing some electrons at an H, which is forced to leave without taking its electrons with it. So it's getting transferred as just a proton. Okay, so the thing about this reaction is it's actually reversible. I could just as easily have given you these two things and said nitrogen, its lone pairs can take an H, steal it right back off of the oxygen and turn it back into OH minus. So I can do arrow pushing for either the forward or the reverse direction. Typically, when we're showing mechanisms, we only show the arrows for how to get over to here, and then these arrows would show you how to get to the next step. But you can always show arrow pushing to get back the way you came from. In the reverse reaction, this thing, is this acting as a base or an acid? Base, right? Because we're showing this as the product of an acid-base reaction, I would call this the conjugate base of NH4. So these two things are a conjugate pair, like this is an acid and this is its conjugate base, or this is a base and that's its conjugate acid. And meanwhile, this thing is the conjugate acid of that base over there. So this is another conjugate pair. So basically, we're looking at two different bases that swap a proton around, and then one of them acts as the acid, like while it's giving up that proton. Okay, so the stronger an acid is, the weaker its conjugate base, and vice versa. Okay. So we can actually have molecules that can act either as an acid or as a base. So water is actually one of those. It can either lose a proton to become OH minus, or it can gain a proton to become H3O plus. Does anyone remember what the name for stuff that does this is? Amphoteric, yep. So water actually has two conjugates. It has a conjugate acid of itself and a conjugate base of itself because it can do either direction. Okay, so we need some way to quantify how strong our acids and bases are. So what we're going to do is look at some hypothetical acid. We're going to call it HA, so a proton stuck to whatever the rest of the acid is, and H2O. Going to react to form A minus and H3O plus. Okay, so pretty much like Gen Chem 2 was all about this acid-base equilibrium stuff. So the equilibrium constant for this, if you remember from Gen Chem, KEQ, is going to be the product, the product of all of the concentrations of stuff on this side. So concentration is in square brackets. So A minus H3O plus all over HA H2O. But because concentration of H2O is more or less constant, you're doing this stuff in water. The amount of water is not like changing appreciably because there's a lot more of it. We're going to treat this as a constant. And so we're going to define Ka is KEQ times, getting that term out from under the bottom of the fraction here, is A minus H3O plus all over HA. Okay, so basically the the bigger the equilibrium constant is, the more this is happening, which means the more HA gives up its proton, which means the more acidic it is, because it's giving up protons like crazy, which means the bigger Ka is going to be. Okay, so more acidic, bigger KQ, bigger Ka. Problem is that the acids that we're going to see cover such a huge range in strength. Like some of them more or less go like exclusively to products. Some of them more or less stay exclusively over here. So we're going to cover orders and orders of magnitude difference in like where Ka could be. So what we really need is some way to make this human manageable number sizes. So we do the same trick that we actually use for like proton concentration. If you remember, instead of just looking at like the concentration of H, we use the P of H. So like pH is a log of the number that we're trying to look at. So pKa is going to be negative log of Ka. So we know that bigger Kas go with stronger acids. If we're taking the negative of that, of the log, then some more acidic, bigger KQ, bigger Ka, smaller pKa. So the stronger acids have lower pKa values. Gesundheit. Okay. So let me just erase the other side of the board real quick and I'll put up some examples. Okay, so a lot of this math stuff is just sort of if you're curious where it's coming from. We're not going to actually do any like derivations of Ka values, but Sapling might ask you to calculate some stuff, but the exams won't. Okay, so there's a whole big table of pKa values in the textbook in chapter 3. And the thing to remember is that they only show you the pKa and the acid. They don't explicitly draw the conjugate base, but you can figure out what the conjugate base is because you just have to pull a proton off of it. So for example, hydroiodic acid, HI, its conjugate base is that missing a proton, so it'd be I minus. pKa of negative 10 on that one. Negative 1.7 is the pKa of H3O plus. Once that loses a proton, it just goes to water. pKa of 9.3 is NH4 plus, which once it loses a proton becomes NH3. And then pKa of 15.7 is H2O, which becomes, we already know, HO minus once it loses a proton. Okay, so on the exam, I will give you a table of pK values on the front cover. I don't expect you to memorize them, but it is sometimes helpful to have a feel for which things have like higher or lower numbers, which are more or less acidic than other stuff that we're looking at. So we know that this thing, pK of 15.7, is less of an acid than, say, H3O plus, which totally makes sense. This one has 3 protons that it's got to offload. This one just has the 2. And both of them are weaker acids than HI, which really wants to lose a proton. Okay, so this one's strongest. This one, out of what I've drawn up here, is the weakest acid. But we know that So here, strongest acid. But we know that strongest acids have weaker conjugate bases and vice versa. So out of the conjugate bases over here, this one is the strongest conjugate base, OH minus. So this thing really wants to get its proton back. I minus doesn't care. It's perfectly fine like it is. Okay, so a lot of the time we're looking more at base strength than acid strength. And so it sort of helps to think of pKa like the bigger the number is, the more that conjugate base really wants to get its proton back so it can go back to being the neutral or whatever the starting acid form was. Okay, so we can use these to calculate equilibrium because it turns out if you have some reaction between an acid and a conjugate base, and this should only take a couple minutes here. If these two guys are swapping a proton around, so like kind of like this example that I showed over here with OH minus and NH4 plus, turns out you can calculate the equilibrium constant even though water itself is not explicitly involved. So you can do 10 to the pKa of whatever BH is minus the pKa of whatever AH is. So you would look up whatever BH and AH are, like these are going to be two different acids, look those up in the pKa table, subtract their pKa's from each other, and then 10 to that power will give you the equilibrium constant. So for example, H3C minus and water okay, so I didn't list this one in the acid table that I sort of excerpted here, but its pKa is going to be a whopping 60. That's actually one of the strongest bases and weakest acids we'll ever look at in this course. Water, we already know, is 15.7. So right off the bat, we can say this is the weakest acid. We know that the equilibrium is going to favor the weaker acid and the weaker base. Which means that products are going to be favored. So you always tilt the balance towards the weaker acid and the weaker base. So in other words, you want the acid to have the higher pKa because that's the weaker acid. But we can calculate how much the balance tips in favor of products by saying, okay, the KAQ for this reaction is going to be 10 to the 60 minus 15.7 is 10 to the 44.3. I didn't bother calculating that out because it's huge. So as soon as you put H3C minus anywhere near water, it's just immediately going to rip off a proton. You'll have pretty much nothing but products left at that point, which is annoying if you're trying to do this reaction and you accidentally get some water in there. Okay, so I sort of skimmed through the last part of bottom of page 6, but that should be enough that you can answer questions about which side is favored equilibrium in the equilibrium on products or reactants.
Just a question about some